Okay, so what can make molecules more basic? Well, really, for the most part, whatever makes them unstable is going to make them more desperate to seek out a proton and go grab it faster, okay? So, what do I want to say here? Well, that's pretty much it. I guess I'll say the big takeaway for bases is usually the more, I guess I should say the less stable the base, the more it wants a proton. Now there are a few examples where this isn't quite true, but usually this is how it works, okay? So this is a good guideline to start. Okay, so we have base A here and base B, and you might recognize it from our acid video where we drew these as the conjugate bases, okay? So here they give us the base to start off with, and the question is, which one of these, A or B, is more basic? Well, base A has resonance so I'm just going to say other resonance structure because I'm a little bit lazy. We've already drawn these, right? So base A has resonance stabilization. Okay, so this is more stable than base B, okay? Because it's more stable, and the reason why it's more stable is because its electron, its charge is delocalized. It's not as desperate to go out and grab a proton, okay? So that's one way you could think about this. The other way you could think about it is what part of a base grabs a proton? Well, usually it's a lone pair. Sometimes it's a pi bond, but usually it's a lone pair. So let's actually draw this out. Let's say I have a proton right here. What part of this base in base B grabs the proton? Well, that's the lone pair. So the lone pair grabs the proton. Okay, let me rephrase. So not only do you want to think about it in terms of stability, but you want to think about it also in terms of availability of a lone pair to go and grab a proton. So here, this lone pair and the other two lone pairs are always localized at that oxygen, okay? So not only is that making that oxygen atom, unstable, but because you have so much electron density in that area, those electrons are more willing to kind of jump out and go grab a proton, okay? So let's look at the electrons in base A. So not only did we say it was more stable, so it was less desperate, if you will, to go grab a proton, but you also need to remember that resonance delocalizes electrons. So here in this resonance structure, this oxygen is negative, and in the other resonance structure, this oxygen will be negative. But remember, technically, only the hybrid exists. So really, you kind of have half of a negative charge, if you will, on both oxygens, okay? And because those lone pairs are being delocalized between both oxygens, they aren't able to kind of mount an attack on a proton because they aren't localized to one spot, okay? So the more delocalized your electrons are, the harder it is for them to go grab a proton. They're involved in resonance, okay? So those are the two ways I can think about it. And they get you the same answer either way, where base B is more able or more willing or more desperate, however you want to phrase it, to go grab a proton. So this is more basic. Okay, So let's look at this. Okay, so again, there's two ways we can think about it. We can kind of think about it in terms of stability, which of course I love doing that, where again, the less stable the molecule is, the more it's like, I'm freaking out, I hate this, what can I do to become more stable? And one of those options when you're an anion is to grab a proton, okay? So this is the least stable base, and therefore it's the most desperate to grab a proton, and so you could think about it like that. I don't know how to spell desperate. Yes, I do. Haha, most desperate to grab a proton. I'm a very bad speller if you haven't noticed. Okay? Now, and of course the fluorine, which is the most electronegative atom, is the most stable. So it's, you know, it's just sort of like, I don't really need as much. I'm not as desperate to go grab a proton. It might be nice, but I'm not like desperate about it, okay? But the other way to look at this, and it'll still give you the same answer, is in terms of what electronegativity means. So if you have fluorine, which is the most electronegative, that means that it wants electron density towards it, okay? If it's kind of hogging the electrons and keeping it close into its, close to its nucleus, then it's not allowing those electrons as easily to go grab a proton. Because in order to grab a proton with a lone pair, that atom has to be willing to essentially donate a lone pair into a bond with a new atom. And so because fluorine is the most electronegative, in other words, it's an electron hog, if you will, it's not willing to share and it's not willing to donate those electrons needed to form the bond to that proton in the first place. Okay, so how should I write that? I'll write that in another color because it's kind of a different point. But again, it still gets you to the same point, which is fluorine is not going to be as willing to grab a proton. So it's more electronegative, therefore does not want to donate one of its lone pair into a bond which would form, well, how should I phrase that? Let's just say more electronegative, therefore does not want to donate its lone pair into a bond to a proton, okay? And this is all relative, of course. So this molecule over here is the least electronegative and therefore the most willing to donate a lone pair into a bond with a proton, okay? So if we had to rank these, let's say, here we go. So this is the most basic. In fact, let me use numbering here. So 4 equals most basic, 1 equals least basic. All right, so this is 4, 3, 2, 1. Because it's really a continuum of what we've been talking about with the two extremes on the left and the right. Okay, not being attached to an electron withdrawing group. So really, again, this kind of harps back to point number 1, which is resonance. Resonance is just the delocalization of electrons through pi bonds, right? inductive effects, which happen when you have atoms that are very electronegative and cause a strong dipole through sigma bonds, also delocalize electrons, not to as much of an extent as resonance, but still significantly enough for us to make comparisons. So again, for the same reason, these fluorines are delocalizing this negative charge away from the oxygen. Okay, that's doing two things, and we've kind of already talked about this in resonance. One is it's making that oxygen more stable, and so the molecule is a little bit less desperate to get out of the situation, because it's like, well, I mean, I'm not in the best situation, but I'm still kind of stable relative to this other molecule, which is not stabilized through any sort of means, and so it's very desperate to kind of change its situation, if you will. But again, the other thing has to do with delocalization. So if we delocalize that negative charge, we're delocalizing the electrons, which means those electrons are not as localized, which is what you need in order for them to grab a proton. They're not as available because they're kind of being dragged across the molecule, if you will. So, instead of writing all that down again, I'm going to say this one is more basic. I'm going to let you guys pause the video and you can write all those notes. But it's pretty much saying the same thing as number one, just in a different way. All right, having a smaller atomic radius. Again, right, this molecule here where the oxygen has a negative charge versus sulfur with a negative charge, right? So oxygen having a negative charge is not as stable as sulfur having a negative charge because sulfur is larger, so it can accommodate an extra electron more easily than oxygen would. So again, the way I like to think about it is desperation. So the oxygen is going to be more into seeking out a proton than the sulfur is. Anything else? I think that's pretty much it for that one. So let's say more basic. Alrighty, so this is our last question here, example 13E. Which of the following molecules is the most basic? A, B, C, or D? Okay, so let's see what we've got here. We've got a negative on a nitrogen, a negative on an oxygen, a negative on a nitrogen, and a negative on an oxygen. So all of them have a -1 charge, okay, so that's not the differing factor here. The differing factor seems to be the atom that our negative charge lives on. A negative on a nitrogen versus a negative on an oxygen. Now, just based off of that, what's more stable, having a negative on an oxygen or having a negative on a nitrogen? Well, it's more stable to have a negative on oxygen because oxygen's more electronegative. Okay, but we have something else we need to look at, which is with these two here, we have resonance. So here, there's a negative on the nitrogen, so that means there's 2 lone pairs on that nitrogen. So we drew those in, and a lone pair goes to a bond, which forces a bond to a lone pair. So our other resonance structure will look like this. Okay, and then when it comes to the oxygen, we have 3 lone pairs, and one of them will go into a bond, which forces a bond to a lone pair. And so our molecule will now look like this. Okay, so both of these have two resonance structures, which means they're resonance stabilized. Okay, so that means that those lone pairs that need to go out and grab a proton are delocalized to some degree. Whereas C and D, neither of those have resonance, so the lone pairs are just chilling on their atom, and they have nothing else to do, they have nowhere else to go, and so they are very available to go out and grab a proton. So comparing nitrogen versus oxygen with no resonance, we know that nitrogen is less stable, so it is going to be less stable base than this molecule, which means therefore that is a better base. Okay, it's more desperate to grab those protons. Okay, in fact, it's more willing because nitrogen is less electronegative. It's not so much of an electron hog, which means it's more willing to donate a lone pair to put into a bond to a proton. And that's it for this video.